Okay, so we've looked at Cosini-Kármán and talked about how we can use that to predict hydraulic conductivity of coarse-grained soils. So let's talk about how we measure hydraulic conductivity. There's two ways to measure hydraulic conductivity. One's to do in the lab and one's to do it in the field. We're going to talk specifically about lab testing. So the advantages of lab testing are that we've got good control of the boundary conditions, both the stress boundary conditions and the drainage boundary conditions, so we can do a much better controlled test, so we know more about what's going on there. Generally less expensive than field tests, although we got to get the samples. The big disadvantages are, yeah, well, we're testing a really teeny volume of the soil, you know, which is not necessarily representative of the field. In fact, we'll show in a minute why it can be very, very unrepresentative of the field. So it's not going to capture the variety of the field. And if we're using coarse-grained soils, there's no way we're going to get a representative sample out of the field unless we're using some really exotic sampling methods, which just are used only for research. These methods are suitable for clay liner applications because the clay liners are manufactured soils, and we're going to manufacture them in the lab in a way that's similar to the way we're going to manufacture them in the field. So that they're fairly good tests to use on compacted clay soils, and they're really good for providing control over the compaction and testing procedures. And they're really important in doing quality control for liner systems. So we're going to spend a fair amount of time talking about liner systems. And the fine-grained soils in the field, when we're doing QC in the field, we can actually go back in the field in a liner and take samples and bring them back to the lab to test. So we can use compaction tests in the lab to predict the field hydraulic conductivity, and then we can go out and take QC samples out of the field and test them in the lab fairly reasonably, because we can take those undisturbed samples for the clay. So these are really good techniques for doing quality control and design of clay liner systems. They're not such great techniques for figuring out, how well is the water going to be flowing out of a well or across some place. You're better in those cases than actually doing pump tests in a field to get a global hydraulic conductivity for the field. All right, so let's talk about these. There's two fluid boundary conditions we can use for tests. One is the constant head test, which is just the Darcy test that was done. And we've already talked about that. We're just keeping delta H constant, H constant, L's constant. All we got to do is measure Q. We just got some system for measuring Q. It's usually what we're measuring is the volume collected over a period of time. We're actually usually measuring volume and just measuring time and calculating Q. And so we just wait for that to, we just figure out how long it takes for a certain amount to be collected in our little graduated cylinder, whatever we're using, and we get Q is equal to KIA. And so then we just solve for K. K is equal to Q over 8 times I, and we know the hydraulic conductivity. If we know the hydraulic gradient, we can expand it out as L over, we just expanded the hydraulic gradient out as L over delta H. So we can run these tests at different hydraulic gradients to see if there's any change over hydraulic gradient. And generally, there's a good discussion of this in your lab. There's some evidence for very, very low hydraulic hydraulic gradients for clay soils that they may deviate from Darcy's equation, but there's also later published data that indicates that might just be an artifact of the test. So for all practical purposes, I think we find that the Darcy's equation works fine for fine-grained soils, coarse-grained soils. It doesn't seem to be a problem. The trouble with this test, the big problem with this test, when we're testing very, very fine-grained soils that have very low hydraulic conductivity, is that it can take a long time to collect enough water to measure it, and if you've got things like evaporation losses and other things, it can be really, really hard to measure really small quantities of flow. So another test method that was developed to do that is called the falling head test. In this case, you start with a fixed fluid boundary at the bottom. You have a fixed head at the bottom. You have a fairly small tube at the top, and you start up at some high head, You know the cross-sectional area of the tube as well as the cross-sectional area of the sample. You start off at a certain delta H, and then you just open up the stopcock and you let this thing flow, and then you measure a delta H later. What's nice about this one is you can use a really, really small tube so that you can get a really accurate measure of the volume because you're using a really small diameter tube. But the hydraulic gradient, the hydraulic gradient in the head is changing the whole time. So if you solve hydraulically for the boundary conditions for this one, you can show that the hydraulic gradient is equal to the log of the ratio of the initial head divided by the final head times the ratio of the area of the two tubes, little a over big A, times the length divided by T. So you can prove to yourself that that's true. This used to be a really important test for testing the hydraulic conductivity for clay soils because it's one of the main ones we can use for those really low permeability soils. Turns out now with flex wall permeameters, which we're going to talk about in a minute, we've kind of eliminated the need to do that. So we don't do this test as much as anymore, although it sometimes is done during consolidation testing. So it's still a viable test. So let's talk about the permeameters. There's two basic classes of permeameters. There's rigid wall permeameters and flexible wall permeameters. So rigid wall permeameters are, on the left you see a lucite or plastic tube that is holding a soil. Those of you who have been in our geotech lab, we have these big GNOR permeameters there on the wall that we use for undergraduate classes. A classic picture of a rigid wall permeameter. And the issue with the rigid wall permeameter is there can be things going along the edge between the soil and the edge that really aren't representative of the soil itself. The second one, this is a compaction mold permeameter. And if you can see at the bottom, this is just a compaction mold. So this is the kind of mold you would use to test hydraulic conductivity of compacted clay. You just compact your clay liner in there, strike it off, do your Proctor test, and you stick the whole Proctor sample inside the permeameter and test it. And so the biggest issues with these are that you don't have control over the stress because you don't know what's going on, and also there's some issues with potentials for sidewall leakage and stuff like that. A flexible wall permeameter looks a lot like a triaxial test, except instead of measuring a strength, we just have the sample inside a flexible membrane here, and it's inside a cell, so we can put cell pressure on the outside of the cell, so we can have a sigma 1 equal to sigma 3, and we can confine the sample, and it does two things. It really seals the sides of the sample up of the membrane up against the sample, so we don't have to worry about sidewall leakage. Plus, now we can test the soil under different stress conditions. So if we're worried about what's going to happen at the bottom of the dam or the bottom of the landfill liner as it gets filled up, and the stress, total stress in the sample is going up, we can measure the hydraulic conductivity at different stress levels, which means different void ratio. So that's a nice advantage of that. So this is what the compaction mold permeameter looks like. You can test the samples directly from the mold. That's really nice. You can run it as a constant head test or a falling head test. It's pretty quick. There is an issue with sidewall leakage because particularly if your sample shrinks at all, which generally doesn't do for water, but if you permeate a sample with something that's not water, it can shrink. If it shrinks, then you can get a lot of flow down the sidewalls, which isn't represented. The other issue is we say the sample may not be saturated. I can tell you the sample won't be saturated. The saturation might be pretty high, might be 85% or higher, but you're going to have trapped air in it. You will not have a saturated sample. That may be fine. That may be representative of the situation you're using. And then finally, we don't have any confining stress, so that we really don't know what the state of stress of the sample is. There is a variant on this one to get around the problem of sidewall leakage, and that is you put a little ring inside here that divides the inside of the specimen from the outside of the specimen. So the idea is that you've got two different flow paths. You've got one flow path here inside, and you've got another flow path outside, and that little ring is set up so that the area inside the ring is equal to the area outside the ring. So if you don't have any sidewall leakage, and then you're gonna collect your effluent separately from the inside ring and the outside ring. So if you don't have any sidewall leakage, then you have the same volume of those two. If you have a lot more volume coming out of the outside one than the inside one, then you know you got a bad test. So it's a way to get around. It's a way to identify sidewall leakage. These were used quite a bit in the 90s. I think people found out for standard testing, if they compacted the soil well, it wasn't an issue, and I think they're pretty much used only for research now. In fact, they may have been used only for research back then. So I already said that. You can use a consolidation cell. You can test the hydraulic conductivity while you're consolidating. It has to be a fixed ring cell that has no flow out the bottom, where you got control of the flow in the bottom. And all you do is you put a standpipe. You stick a standpipe into the cell at the bottom in the middle of consolidation head. You fill it full of water and you run a falling head test. So in this case, the water is actually going to be flowing up through the sample, and this is done quite a bit. So the soil sample, you can cut it from if you want to test a compacted clay liner, you can cut it from a sample that you got from the field, so you can do a field QC check as well as a test from a lab compacted sample. These are usually run as falling head tests because they're usually run on low hydraulic conductivity material, so you got to have a pretty high head to do it. So they're usually run as falling head tests. It's simple, but obviously slower than doing the compaction mold test. There's really not an issue with sidewall leakage because you're pressing on the soil, so you've got that problem eliminated. And the soil may not be saturated. There's a better chance that it's saturated than during the compaction mold test. And you do have control of the vertical stress, so that you can change you can test hydraulic conductivity at different void ratios and different stresses. Then this has become the workhorse of methods now. I think it's by far the most common one to do, which is the flex wall test. And again, you're using let's see, I can highlight this thing and put it in blue. So this is inside a triaxial cell, so this area is all filled with water all around. You put a cell pressure on there. You've got a membrane around the sides of the sample, so that seals the sample off. And then you've got control of the flow in the top, separate from the flow in the bottom. So now you can control the stresses on the sample. You can also hook this thing up. You hook this up to your triaxial panel, and you've got control over the head on the top of the bottom, and you can put a really high height gradient on this. So you can take a soil that has a very low hydraulic conductivity, just put a big gradient on it, and you get a decent amount of flow, so you don't have to do a falling head test where you've got the flows are so small that they're difficult to measure. So this has become a really, really popular method. The samples can be undisturbed samples from the field. They can be recompacted samples. You can use any kind of sample you want. Obviously, if it's a coarse grain soil, you've got to worry about the coarse grains. How are you going to get a representative coarse grain soil? You can back pressure saturate it. You can ensure that you get a saturated hydraulic conductivity. It does take a lot longer to set up than almost any of the other tests, because you've got to basically set up a triaxial test, and you've got to back pressure saturate it. Sidewall leakage isn't an issue. And we basically don't have to run falling head tests anymore. We almost run these as constant head tests. And you got complete control of the stresses. So this has become, by far, I think, the most popular way to do it. It's the ones where you have the best control of what's going on, and you eliminate the issues with falling head tests. I guess the only other one that's run, well, the compaction mold ones are still run quite a bit because they're easy to run. And you can put those on your triaxial panel too. You can run those at really high hydraulic gradients, and you can get flow rates for clay soils out of them pretty easily and stuff too. And so this is just to show you the quality of the different tests. So this is for a kilnite clay, and this is for a fire clay. And here's the compaction curve for the soil, and here's the hydraulic conductivity from both the compaction mold test, the consolidation cell, and the flex wall test. And I think in the world of testing hydraulic conductivity, those numbers are all pretty much the same. This happens to be just a different clay. There's more disparity between the values here, but notice that this is 2 times 10 to the minus 9th to 1 times 10 to the minus 8th, so that's not even one whole order of magnitude change. So in the world of hydraulic connectivity, again, those are actually pretty close numbers. So as long as you're not having sidewall leakage and stuff, you can get pretty good measurements from any one of these tests. The gold standard still is, I'm sure, the flex wall test. So this is the one that people would say gives you the most accurate results, the flex wall test. Okay, so summary of lab tests. These are suitable for characterizing manufactured soils. You can get undisturbed samples of clay soils. Really can't test, well, you can just test samples of gravelly or sandy soils, but there's a real question of what kind of sample disturbance you have and how representative they are of what's going on in the field. They will not capture the variability of field soil conditions, though. And as long as you don't have to not worry about what the applied stress is, then you can do tests for the ridge wall test. They seem to work fine. And the flex wall is by far becoming the most common, and I think that's the gold standard. I finally want to talk very quickly about layered systems. There's a good section in your book about this, talking about layered systems. Flow and layered systems. This will get back out to what the field, why we can't measure hydraulic connectivity for a field level thing by doing a laboratory test. So here's 3 samples with 3 different hydraulic connectivities, and if the water is flowing parallel to the bedding in these, what's constant in this test between each of the soil layers, and what isn't the same? Is the same amount of water going to flow between each soil layer? No. What is constant? L is constant and H constant, so the hydraulic gradient is constant. So that's what's constant in this one. So I1 is equal to I2 is equal to I3. Right? So Q for the first one is equal to KIA, right? Q for the second one is equal to KIA. In this case, A is just H because it's 1 unit into the bore. So those are the equations for the 3 Qs. And if I want to know the equivalent hydraulic connectivity and K for the whole system, well, those 3 Qs added together is equal to the total flow, right? So that would be equal to my equivalent hydraulic connectivity times I times the total height of this particular stratum. You following me? Okay. So I could just write that, well, that's KE times I times the total height is going to be K1 I1 H1 plus K2 I times H2 plus KI3, and the I's go away. I solve for KE, and the I's go away, and I get this, that the equivalent hydraulic connectivity for this system is the summation of K times I divided by the summation of H. I'm sorry, K times H divided by H. So what's going to control the total flow in this one? Remember, how much does hydraulic connectivity vary between different soils? A little bit? Huge orders of magnitude, right? So if one of these soils has an order of magnitude higher hydraulic connectivity than another one, that's what's going to drive the flow. So in this case, the flow is going to be driven by that soil that has the highest hydraulic connectivity, unless the layers are really, really thin, right? So in this case, the high hydraulic connectivity soil is going to control the overall hydraulic connectivity of the system. So let's look at the other problem. Take the same 3 layers, and now we're going to flow water across the boundaries in the other direction. Okay, so what's the same in this system? What's constant in this one?
What's the constant height?
No, there's different. Each soil is a different thickness, right? H is different in each soil. What's constant between the, Well, the total head's the same, but what, are you gonna have different head losses in each one? Yeah, so you're not gonna have, so the heads are gonna be different, the height's gonna be different, the hydraulic gradient's gonna be different, but what has to be the same between all of them?
Fluid, the same kind of fluid.
So it's not only the same kind of fluid, but Q's gotta be the same, right? Whatever comes in the top one's gotta go into the second one's gotta go into the third one, right? So Q or V is the constant in this one, right? So V1 is equal to V2 is equal to V3 is equal to the velocity of the whole system. Right? And we know that V is equal to K times the gradient, right? So, so delta H1, if I knew the head loss in the first one, that's going to be equal to V times H divided by K. And I know that the total head loss is equal to, I do know the total head of the system. I don't know how much head is lost in each one of those things, but I do know the total head, right? So the total head is just equal to the sum of the heads. So the total head change is just equal to the velocity, the sum of the velocities, the velocity times the sum of the H1 over K1. So back up, again, if I want to solve for the apparent K for the whole system, the velocity is going to be equal to this equivalent, some equivalent hydraulic conductivity times some equivalent hydraulic gradient. So that's got to be equal to the equivalent hydraulic conductivity times the total head loss divided by the total height. So I substitute into that the total head loss is going to be just the sum of the I'm just going to substitute this into here, right? And I get that, and I can simplify that down to saying, well, the equivalent hydraulic conductivity for this system is the sum of the thicknesses of the layers divided by the sum of the thickness of each layer divided by the hydraulic conductivity for each layer. Now what's going to control the flow for this system? Again, these K's can vary by orders of magnitude, right? So what's going to control the flow now? Yeah, the lowest hydraulic conductivity is going to control, which you should think about, right? You know, I mean, you go out in the backyard, you want to have a nice pool for your kids, right? What do? You put a piece of visqueen down, you know, holds water really well. Very, very thin, very, very low hydraulic conductivity, right? This is why clay liners work in very thin clay liners can work to capture the flow, to control flow in a landfill or something. All right, and there's a nice section in your, I think, do I give you all these? Oh, I don't give you these numbers. So this is just a numerical exercise. I'm not going to go through the exercise, except I'm going to show the results. So these are reasonable numbers. So you got 10 meters thick sand with 10 to the minus 2 centimeters per second. You got a 1 meter of silt with 10 to the minus 5. You got a different sand that's 5 meters thick and has a K of 10 to the minus 1 centimeters per second. Those are all reasonable numbers, right? So what's the equivalent horizontal hydraulic conductivity? Well, that's this equation. And the equivalent horizontal hydraulic conductivity is going to be 4 times 10 to the minus 2. Right? Which soil is controlling that? The sand at the top. Right? Because it's really thick and has, and notice that hydraulic conductivity is greater than that one because you're getting a fair amount of flow through the sand at the bottom, which has a hydraulic conductivity in order of magnitude higher, but it's only half the thickness. So it's partway between those two, right? What's the equivalent vertical hydraulic conductivity? Well, that's this equation. We plug those numbers in that one, and that is 1.6 times 10 to the minus 4. What's that equal to? That's basically being totally controlled by the silt layer, right? So, if natural soil deposits are generally horizontally bedded, what's your horizontal hydraulic conductivity going to be compared to your vertical hydraulic conductivity for a geologic system? You're almost always going to have a higher horizontal hydraulic conductivity than vertical by orders of magnitude. Now that's not always true because, for instance, on this, we are uphill of the fault here on campus, And that fault has a big gouge layer in it, and the water table up here is only a few feet deep. If you go about 100 feet in that direction, you get the other side of the fault, the water table is like 40 or 50 feet deep. Because that's a horizontal, a vertically oriented aqueduct there, and it's actually, you know, an underwater dam holding the water up on this side of you know, so that you can't have, you know, boundaries. In that case, that boundary is like looking like this, and so there is clearly a, you know, a big boundary, a horizontal boundary to flow in that direction. But generally speaking, we're going to have much higher horizontal hydraulic conductivity for a system in the ground than vertical. Cool. I got 5 minutes to cover the other one. Oh well. We'll see how far we get.